start today's lecture. And I'll go with that. Okay, so let's see. So last time we talked about we're in the middle of talking about group cohomology. HI, GM. Okay, where M is a abelian group with a continuous action with the action of G. Here, right now, G is a discrete group right now. So we went through the Hauscher's special sequence. Let me just quickly recall where we ended last time. So part 6, if H is a normal subgroup of G, and I just want to emphasize that we have a 5-term exact sequence as so. So you first take the H invariant, and then so remember that we have this sort of special sequence which sort of looks like so. So H0, 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 H1, and H1, H0 here. And I'm just going to list all the terms that matters to me. So, and the D2 term goes here. And so the special sequence will go always, the 5-term special sequence will go from this term here, right? I'm sorry, wrong. Can't believe I wrote it wrong. So one of the rules is that somehow in a special sequence, the inner cohomology always goes up. Somehow the inner degree goes up when you move up. So H0, H1. And if you move to the right, the outer degree increases. So then somehow supposedly there was a D0 here, and then there was D1, but those are already taken cohomology off, and now you have D2 here, and you start with this term here, and that embeds into the bigger cohomology, and then you move to this term, G mod H, H1, HM, and then through this D term, this D2 term, you get to H2 of G mod H, invariant by H, and then the whole thing converges to cohomology of G, so just get that. Okay. Like so. And also I want to mention that from the special sequence, we have some more maps to go. Let me just let's try this color as well. Look that up. So I have H0 of some Hn, say here, and this is always sort of the quotient of the big cohomology Hn Gm. And whereas, let me just write it over here. Sorry for that. So Hn of H0. So there's always a natural map from this to Hn of Gm. For any n, so the two boundary things will receive maps from the big cohomology of Gn to that. So namely, I have two maps here. Hn Gm goes. Oh, sorry, this is not surjective, but there's just map. H0 of GH Hn. So this is usually called the restriction map for any n. And similarly, there's a map going the other way from that one. Now I have to line these up. Let's line these up. From, I'm sorry. Oops, I was very confused. So in other words, this is just Hn of Hm of G mod H. So this is usually a restriction of a commutative class from G to H. But when H normal in G, the image lies in the part that's invariant of G mod H. Similarly, I have that map. So Hn of H, invariant of H, there's an inflation map going on that too. just can't make it right today. It's G mod H2G. So there's always an inflation map, like so. But only in degree 1, this is injective. In general, we don't know yet. Okay, so that's all I want to say about special sequences. Okay. Right. So now let's sort of quickly recall. I'm going to use what I learned in sort of earlier. Just kind of recall Shapiro's lemma, which says that if H is a finite index subgroup, then Hi of H of M is isomorphic to you induce your module from H to G and then take homology. Now, I want to use this to explain the following so-called degree shifting technique. Or degree shifting trick. So let me just making it more in terms of more like example. So let's say G is finite, and this G would act on some G module F, and I want to compare. There's a way to compare M with induced representation from the trivial representation. I mean, I think of it as sort of, maybe I just write M underline. So this is just a abelian group. I think this abelian group as I guess a module for the trivial group. Okay, I can use that to the G module. So this is just nothing but just literally functions from M. So function from G to M. And there's a natural map from M to this. Basically sending M to, I think, GM. Sorry, I mean like sending to a function, right? So G maps to GM. Okay. Right. And then now, so of course it's obviously injective, right? So I can definitely get the co-kernel. Let me call it Q. Now I have an exact sequence from M to the induced module to Q. I can take cohomology of that. So for I bigger than 1, or I mean I don't have to, sorry, just for I greater than, maybe, for I greater than equal to 1, I will have a long exact sequence associated to this short exact sequence from M to the induced module to Q. Let me put it in the right place I want to discuss. So I want to do HI of the middle term to start with that. And then this goes on to I cohomology of the Q. And then it goes down to the I plus first cohomology of M. And it goes back to I plus first cohomology of the G of the reduced module. Okay? So I take cohomology of this one. Then by the Shapiro lemma I just explained, this is nothing but HI of the trivial group cohomology. And same here. But these are all 0 because, I mean, the trivial group doesn't have higher cohomology. And then see what we end up getting is that this sort of I plus first cohomology of M is isomorphic to a I's cohomology of another G module. So this is a standard trick in proving things in group cohomology, that you use induction to prove something by inducting on the degree of the cohomology. And this this type of trick will allow you to decrease the degree you are working with. Suppose you prove something for all the degree less than or equal to I. Now you want to prove something about the degree I plus 1. So you use this kind of isomorphism. You just relate this I plus first cohomology with the ith cohomology, and then the thing about ith cohomology will carries over to the ith plus first cohomology. We'll probably see this today, hopefully by the end of this lecture, that we'll use it to prove this local Tate duality. We'll use that. And maybe let me also mention that there's a variant of this. There's a variant. So this is, you can think of it as a kind of a degree lowering, but then you can do the sort of the opposite thing. So that's just say we can consider the so I particularly write this lowercase ind for the I guess I don't really know which one is induced. I think this is induced. This is co-induced. But anyhow, I can also use this to mean M tensor with Z1. Oh, sorry. Z bracket 1. This is just Z. But I won't think of it as kind of a group algebra tensor. So I guess in general, if you have H and G, tensor over ZH and then with ZG. Okay? And then instead of having a map that way, you have a map the other way. And then you can take sort of the kernel of this. Now the row of Q and M are sort of swapped. So if you prove something about the degree I plus 1, then you can deduce things about degree I. So you can shifting degrees both ways if you have some finite index difference. So by the same argument, that you show that M is isomorphic to HI plus 1 GK. So somehow it gives you a way to shift degrees both ways. Okay, good. So that's just sort of kind of a very brief sketch of what degree shifting techniques is. So now I want to switch to the case where that G is a profinite group. For example, of course, what we care the most is the Galois group. But I don't think I will, in this class, talk about the case where M is sort of have some sort of continuous structure, but I will be just focusing on the case where M is just a discrete group, with discrete topology. So usually finite length ZL module. Okay, namely it's a sort of ZL torsion module, finite generated ZL torsion module. Of course, the theory can be extended to the case of finite generated ZL modules with continuous G action, but we're not going to go there. Then I can, the definition of group homology is that this taking the somehow limit over all open compact subgroup of H. You take the H invariant of this M and then take sort of G mod H cohomology. So H, this is an open compact. Maybe I should say open and normal, I guess. You take the limit over all the open normal subgroups G, so that this quotient is now finite. Now we can use the original definition and then take the limit. Then I have the indexes from last time, so basically if you have the indices 1, 2, 6 will still hold here. Holds true. In particular, I think 6 is about Hauschier spectral sequence. So there, I only need to require that H is I need to require that H is a closed subgroup of G. I mean a normal closed normal subgroup. Then the Hauschier spectral sequence still holds true. I'm not going to prove that. But I want to discuss a very special case of a point that I discussed earlier, which will be useful for our later computation. So that's part 3 I discussed. So let me quickly recall what part 3 talked about. Part 3 talked about that if you have some sort of Z mod NZ as a group. So let me not use G to denote it because my G will be a profiling group in a minute. So this will act on a module M, and then we've shown that using an explicit resolution, we show that this is just M. Let me give a generator for this. Let me say the generator is 1. I'm going to use sigma to denote that. Or maybe just write this as generated by sigma. So H0 is definitely invariant under sigma. Then after that, all the odd cohomology of M is given by the elements in M with norm under sigma. So this is just 1 plus, so it's basically sends M to M plus sigma M plus all the way plus sigma M minus 1M. And this divided by sigma minus 1M. And all the even cohomology, degree greater than or equal to 2. I mean, 0 is here. This is all the parts in M that's fixed by sigma, but then divided by the image of the norm, which is of course fixed by M, fixed by sigma. But now I want to, so that was how discussed last time. But now I want to discuss a special case where G is, I guess, Z hat. So so this is inverse limit of Z mod NZ. I'll later on discuss sort of slight variants of this. For example, I take only those N which are somehow not divided by a particular prime P or something, or later variant Z away from P. But somehow but somehow the result is the same. It doesn't really matter that much. I'll say what the invariant will look like in a bit. Okay, and now I say M is sort of N torsion for some N. So in my variant, the only requirement that P does not divide N. That's mine. So there's a variant version we're going to use. So in the variant version, I want M to be a N torsion, but N is not P. So that's sort of. Anyways, so let's look at this case and then see what this direct limit tells us. So let's see. How do I do this? So let's look at, so I want to look at the limit. But then I want to, in the limit, of course, each of the term, I already explained it up here, so that's what it is. But then I have to be careful about the connecting map. So somehow the connecting map for n dividing n prime is that, so you want to maybe somehow take n large enough. So maybe let me just sort of say that eventually I'm going to take limit over all n. So might as well just assume that my n is large enough so that n divided n. Supposedly I have to take invariant under nz here. By this definition, I have to take invariant under the normal, sort of compact normal. This is an open subgroup. But then already said that, okay, I wanted my capital N to divide n, so therefore I don't have to write this. Just like that. Now this goes down to hi of z mod m prime of m. But the upshot of this map, of course, like, if you look at sort of the shape there, these are all the similar shape, but this map is somehow multiplication by n prime over n divided by to the I over 2 floor power. So this is not the isomorphism map you would imagine. For example, I guess if h is odd, if I is odd, say, for example, I equals 1, this will look like invariance under, or maybe we talk about the even cases easier. So for example, let me sort of say what I mean by this. So for example, if I talk about h2, for example, I equals 2. So this would then be equal to m sigma over something goes to m invariant under sigma over something, right? But then this map, if I equals 2, it's not a natural map from m sigma to m sigma, but it's rather it's multiplication by the ratio of n prime over n. But when I is 4, this is going to be multiplication by n prime over n squared, and so on and so forth. So in the limit, because of this, now I have to take a direct limit over some sort of torsion module, and where the maps are given by multiplication by something. So in the limit, because of this sort of this multiplication thing, all the degree, if it's greater than or equal to 2, all vanishes. Oh, equals 0. It all vanishes. So my conclusion is that only the H0 and H1 survive this. And the cohomology we get from this is that of course the H0 is still the invariance. Question? No? Okay. H1 is isomorphic to m over sigma minus 1. Just like that. But somehow you see that you can think of it kind of a limit. When this sort of degree n goes to infinity, this condition sort of just dies. So just m over that. So that's what the cohomology, group cohomology with respect to a profiling group looks like, or at least particularly this d hat looks like, where sigma is a topological generator of the hat. But I just want to make one comment here that I particularly, if you know me, if you look at my writings carefully, I have two isomorphisms. One is this, the other one is this. I always write this mean canonical isomorphism. This means not so canonical isomorphisms. So there's small subtlety here. I wrote this because this depends on the choice of topological generator. Sigma. Basically, if you if you write things in terms of continuous cochains, so if you write this as sort of the cohomology and of sort of continuous cochains of continuous cochains of this group Z hat with values in M, then going this way then this map is evaluation of the the co-cycle at the topological generator sigma. But of course we know Z hat has many topological generators, so somehow you have many ways to write this isomorphism. Nonetheless, if you fix a topological generator, sometimes one is a good canonical good sort of canonical generator. Then of course this is a canonical isomorphism in that sense. So I don't know. Maybe I should write sort of half canonical, half non-canonical somehow. It's not clear. Right. Okay. Are there questions about this? Comments? Okay. So. Yeah, I guess I didn't. Now let's go back a little bit to 6, the Hauscher-Serre spectral sequence. This will be related to what I will talk about later, very soon, about local potentiality. So I want to look at sort of K, a local field. I want to maybe fix some notation. So when I say that means this is a finite extension of QP or the function field at PT. Okay? And I want my coefficients to be to denote by sort of E and OE. And this is my notation. So this is a finite extension of L, such that I want my L to be not equal to the characteristic of K. Namely, when L equals P, K is okay. When L equals P, I only allow K to be a finite extension of QP. I do allow that for my discussion. So my M is a finite length. Excuse me, a finite length LE module with, I guess, sort of continuous GK action. Oh, so the question was about the coefficient. E is just another field, so this is a finite extension of QL. It's a finite extension. So, it's okay to think of the E as just QL. I'm just allowing more general coefficient field, that's all. No, nothing sort of. I mean, of course, one can state it just purely without referring to this sort of the E. Just say a torsion in the Beating group with an action. But for many applications, for arithmetic applications, it's better to have a coefficient field to allow some sort of coefficients. For example, like this. The reason I talk about this is because, for example, modular forms. We talk about sort of, like I said, when we talk, if you want to relate to elliptic curves, of course, like. We take Q coefficient modular forms. But we know for most of the cases, the coefficients for the modular forms are not just rational numbers. they're in sort of in some algebraic extension of Q. So therefore, the corresponding coefficient will not be just sort of QL, be sort of any Q. Okay, so that's a setup, and now I want to look at sort of let me maybe, but for this discussion here, however, I want to assume L not equal to P. I'll make comment on that in a bit. So of course we know that, we know that there's exact sequence, obvious exact sequence. There's an inertial subgroup K, and the quotient is the Galois group of the residue field. Now I want to use the Hauser spectral sequence to this situation, or rather somehow the 5-term exact sequence to the case. So for this app, so I will get what? I'll get sort of H1 of the outer cohomology of that part that's sort of invariant under IK, and the part H1, and then goes on to talk about H1 of IK of M of GK. Okay? Supposedly, I should go to the next term, which is H2 of GK KF. Right? So that's a 5 term, so there's a 4th term of that, and there's another term later on. But already in this term, we know that this is Z hat. The Galois group of finite field is Z hat. And we just proved that the H2 of Z hat is always 0. So this exact sequence stops here. So we just have 3 terms in this particular case. This is a very important case for us. So we have names for these. So the first part is usually called the unramified part. So sometimes we write H1 unramified GK. So this is called the unramified part. Whereas this side is usually called the singular part. Of the cohomology. And that's why that's why I assume L not equal to P here. This exact sequence still holds if L equals P and K is finite extent QP. But in that case, it's how should I put this? So this exact sequence still holds, but then somehow it's not a right way to study the group cohomology. Let's put it this way. So only when L not equal to P, this is the correct way to think about it. So when L equals P, we should use some sort of P ad hoc theory techniques to do that. We'll get to that much later. So therefore, usually we rewrite this as sort of locally just a handy way of writing this. So somehow I separate the part that which is the first part being the unramified part, the last part being singular part. How should I put this? So, but maybe let me explain a little bit why. Let me explain where this notion comes from. So assume, I think it comes from the following. So assume that the GK action on M is unramified. Okay. So when people study Galois representations, we usually study those Galois representations which is unramified at almost all places. So this is one of the places we look at for unramified places. And what I'm trying to say? Okay. So what is the class sort of C in H1 GKM? We define it as an X group, right? It's defined as an X group for the trivial representation. So let me maybe assume that M is a vector space over, say, FL. Okay, just make things simple. So therefore, this is the extension of the trivial representation with M. So that's basically how we define a group cohomology. There's nothing. And I can write it down what this extension is, in the sense that this is sort of 0 goes to M. Remember the extensions? I know the way I remember is always swap these two when you put in the exact sequence. Okay, so this GK will act here in the middle. So this is the extension of the trivial representation by M. The middle guy carries an action of GK. So for every class in H1 or in X, there's another way to express this X as an extension of two Galois representations. Okay, and so this EC is unramified if and only if your class is in the H1 unramified. I guess one way is very easy to see, in the sense that if it's come from H1 unramified, because H1 unramified comes from a H1 of the finite field, and therefore you already get an extension of representations of Galois group of the finite field. Of course, you can think of it as a Galois representation of the entire group, a Galois group. So therefore, you know that if C belongs here, instead this is unramified. And the other way is sort of similar. Questions? So that's why the first part is called unramified in the traditional sense. So, final condition, final notation before I enter. So this is it's very important, I guess, in my opinion. Let's introduce the last one, Pontryagin dual. For N and OE module. So this was a coefficient. I want to write N star to be Hom as group. Well, I mean, maybe let's just do only, because finite length. Because we're just going to be focusing on finite length case. So the Pontryagin dual is just for Hom of N to Z. E mod OE. Of course, you have learned Pontryagin dual for Q mod Z for Abelian groups. It's sort of similar. You just add a coefficient to that. There's nothing sort of fancy about this. Now I can state the main theorem for local Tate duality. So let M be a finite length OE module with continuous GK action. Maybe say 0 for I equals 0, 1, or 2. This cohomology is a finite length OE module. And all the higher cohomology vanishes. The reason one is that for I equals 0, 1, 2, there's a canonical and functorial perfect pairing. The following that you have. Maybe I should say OE linear, but it's obvious somehow. It's obvious. OE linear. So I take the ith cohomology of M. This is 2 minus ith cohomology of punctuation duo of M, but then I have a Tate twist here. Remember, this is a Tate twist. And then I can take the so-called cut product of the 2 cohomology group. I get to E mod OE 1, twist by 1, and this is isomorphic to E mod OE. So in particular, because this is a perfect pairing, I can say one is equal to dual of the punctuation dual of the other. So in particular, Hi of GK is isomorphic to H2 minus I of GK. So punctuation dual and Tate twist, and then punctuation dual again. Somebody like to think of this as Tate dual, but anyhow, it's up to you. I'm just going to write star 1. Secondly, I erased it. I shouldn't have erased it. But anyway, when L not equal to P, under the local duality, the exact sequence I just erased here, star, is somehow self-dual in the following sense. So I just repeated what the star it was. Now I want to do the same thing for the dual. But then there's another dual here, so I want to start from the right to write this H1 unramified GK. Because I want to dual again, somehow this becomes a quotient. For M star 1, this is supposed to be the sub, but then if I dual, this becomes a quotient. Or maybe I should have. Anyways. Well, you know what? Let me not take the dual first. Don't copy yet. Just don't copy the arrows. Okay. Don't copy the arrows. Okay. Other things you can copy. Remember, this was the exact sequence for M. The bottom one was the exact sequence for M dual 1. And now, somehow I wrote it the other way around. So I found it this way because the arrow goes this way. Okay, now I want to dual at the bottom exact sequence. So if I dual, I change direction of all the arrows. Now things goes in the same direction as above. Okay? And the local Tate duality says the middle two terms are isomorphic canonically. And what I'm saying is that somehow all of these terms exactly matches up. Okay. In particular, what I'm seeing is that this term, if I pair with this term here, I must get 0. Somehow, in the sense that this term, via this, viewed as a functional on this thing here, exactly kills the sub-object in here. So then whatever this thing maps down here is 0, so it comes on here. Okay. So in other words, this unrarified part. Maybe I'll have this line here. No, I didn't. So this is the exact annihilator of this HI1 unrarified. And somehow the two event sequence somehow is self-dual in some sense. Anyways. That's that. I'll prove these. Well, partially. Let's say last part is Euler characteristic. So I can define the Euler characteristic to be alternating sum of the length of the cohomology. Take the Euler characteristic, and I get take the alternating sum of the length of the cohomology groups. So this is 0 if L not equal to P. I guess somehow in this L not equal to P case, you will see that things are a lot easier. There's a number here that's equal to the degree of K over QP times the length of OL M. If L equals to P. And of course, by our assumption that K must be finite over QP. So this is equal to this number. I mean, if you are, I guess the best way to memorize is that forget about length. Just think of a vector K as vector space over FP, right? So this is a dimension of M. But somehow for each degree over QP, you have a minus dimension of M. Minus dimension of M means that it will add it on to the H1 of the term. Because we'll see later on, usually H0 and H2 are trivial. Then H1 is usually a non-trivial one. Maybe another sort of comment why somehow we excluded the case where K is why we exclude the case where L equals P, and then K is a finite extension of FP double parenthesis T. So why do I exclude the case where L equals P and then K just say equals to FPT? Well, that's because somehow supposedly, it's a formula like that, I would have K over some FPT, right? But we know that we can always find a sort of large enough extension, like, for example, this is also another sort of extension, and this degree is n. I can make this n as large as possible. So this will be infinite, in some sense. So therefore, basically that's because the corresponding H1 is infinite. So there's no way to kind of measure it. So I'll stop here. Okay. So let's sort of, for this hour, we're going to try to kind of prove this tape local duality. But maybe before that, let's just do an example. And also, I think it's not only an example. I think this is a very important calculation we all have to know how to do, I think. That is that when this M is unramified, my understanding is that not only we need to know not only we need to know what the theorem states, we also have to know, like in special cases, how each of the terms can be computed and why this is true in special cases as well. That's somehow my understanding of how we should study mathematics, I guess. So let's see. So let's do an unrepetitive calculation. So assume that the GK action on M vectors through the residue field. So basically, the initial group acts trivially on M. That's what I'm saying. And then I want to compute it in the case L not equal to P. So let's see. So maybe write down this thing here. GK. So we're going to compute directly using this. And somehow maybe sort of convince you that under this exact sequence, things are dual to each other. Under this exact sequence, or under this so-called local duality, this exact sequence is dual to itself. Except this. Okay, so let's maybe compute this part first. And what is this? This is by definition, just go back to the definition. So GK, K of M. Supposedly I have to take the invariant under the initial group, but somehow we're in the unrepetitive case, so I can just basically ignore that. Okay? And now we know that this is a Frobenius K. Can I use another letter? I mean, like maybe phi K. Phi K is Frobenius, okay? So this is a pro-sticker group generated by the Frobenius phi K, say. Or maybe just phi, for simplicity, okay? And we just, I guess last lecture we just talked about what the common should be. So this is the same as quotient by v minus 1. So that's relatively easy to compute, H1. Now, let's compute a H1 thing, singular part. This is what? This is H1 of, first of all, take an initial group of M. And then take, I can just sort of take phi equals the invariant part. I mean, it's supposed to be invariant under the Galois group with the residue field, but somehow it's just take the phi invariant part. But then I have to compute the inner part, this H1. Now we use the fact that this group acts trivially on M. So H1 is the same as Hom. Okay. And moreover, we're talking about the L-logic things, right? And so basically my M is the L infinite torsion, I say. But inside IK, remember that, let me just write it over here. Inside IK, I have a well inertia. IK has the following structure. Remember? And this is pro P. We talked about this is pro P. And this is sort of a hum into a sort of L torsion vector space. So the pro P part definitely goes trivially into the image. So this will definitely factor through this. And this is Z hat P1. Right? Now, by the same argument, and this is a product of all the Z L prime, say, for different L primes. But the only one thing that matters, which is the L part. So let me just continue it over here. So this is the hum of ZL1. Okay. So now we're much happier. So this is just M inverse. Let me say that everyone should know how to do this calculation. Okay? So what do we need to prove? I computed the H1 thing of this one, and H1 unrepetitive of this one. But actually under that isomorphism, I want to want to show the following. I want to show H1 unramified. Let's just quickly recall what I want to show. This is unramified part is isomorphic to the H1 thing of GK M dual 1 dual. Right? That's what I want to show. I can be the H1 thing of M, but not M dual 1, so I just have to replace this by the just plug in M equals just plug so let's just do this. Basically replacing this M by M dual twist by 1. So this is just sort of M dual twist by 1, then twist by minus 1, and then P minus 1. This is M dual. So therefore, I just need to show, or at least convince you that this is dual to this one. Right? I just need to show these two are dual to each other. But this is some sort of a general fact. This is a general argument, not fact, but somehow a general argument that, you have your M goes to M. On this side you have, how should I put this? I mean, okay, over here, I want to take phi minus 1 map. Same here. And what I have is these are dual to each other. Okay? But note that the arrow here, I put it the other way, the other direction. So the co-kernel of this one is automatically dual to the kernel of this one. So that's the situation we're looking at. In the sense that, or maybe, how should I put this? Or, I don't even know how to do this. Okay, just 1 second. Let me think how to say this. Okay, so maybe here's a kind of a proof of this. So we definitely have 0 goes to p minus equals 1 goes to m, p minus 1 goes to m over p minus 1m, right? I have this exact sequence. I can dual the entire exact sequence. Then I will get, if I dual the entire exact sequence, I will get this, sorry. I just reverse all the errors. If I do the entire exact sequence, I don't have to change terms. I just change direction of the arrows and then put duals on each of the terms. But now we know that this kernel of this one, there's another way to describe it, which is sort of m dual 1, f equals 1. So these two must be the same. Okay? So these two must be the same. So therefore, we see that in this explicit way, these two are somehow isomorphic. Of course, except I didn't quite prove that this is given by the Cobb product. We'll get to the proof of that. So this should somehow convince you that this exact sequence is dual to each other. Yes? Dual. So the question was the. Contraction dual, so contraction dual is self-dual. Yeah. Contraction dual is self-dual. So in general, any sort of OE module is naturally, if you dual twice, it's out. Right. Yes. Should have said that. Okay. So this is just some sort of calculation that convinces you, hopefully convince you that this is a reasonable statement. And in fact, I leave in the homework, one of the problems is that after you prove, after you show that H1 unramified for M and H1 unramified for M dual 1, they pair to trivial. All you need to do at the end is to show this and this thing have the same size. Of course, they're kind of you have I guess one way to make the dual of them, so they must be of the same size. So therefore, you can from that to deduce that the local duality will somehow make this exact sequence, change this exact sequence to itself. Anyways, good? So just some sort of warm up. The most important thing I want to say is this part of the calculation. From H1, making it into half, and then bring it to this DL1, and then do this. Okay? That's somehow, hopefully, I convey that this is sort of the important part of the argument. Or this is somehow a very important part that the calculation you should be able to do. So in fact, the actual proof of this local state duality is sort of somehow in some cases similar. So proof of the local duality.
Excuse me. Can you repeat the definition of tape twist?
Oh, tape twist is just tensor with how should I put this? DL1. So basically, you want to understand what the Galois group, how Galois group acts on this. So basically, it's G of zeta L to the n is equal to zeta L of chi. Or like, think of this as action chi of the L space. And then for any m, M1 will mean that M tensor with the L. So basically, it's treating the Galois action by the cyclotomic character. It will twist. So the Frobenius will be. So the Frobenius sort of Bk will be multiplied by Q inverse. I take geometric Frobenius, or Q is a relativism, or maybe number over Kk. So here, here phi equals 1 is outside, so I don't touch it yet. So luckily somehow over here, these two just cancel. I don't touch it yet. Does that make sense? So here you have 1 and inverse, so they cancel. At the end of the day, I don't have twist anymore. But later on, we'll see somewhere we do need it. I don't remember whether I need it or not. But yeah, so luckily in the way we write it, we don't have to. For some calculation, we do need to. Or maybe this is what you want me to say. I could be wrong. I have to think carefully. So this is equal to that. If that's your asking. So this is equal to that. Am I right?
So L equals P is not, there's no
So if L equals P, so there's one step here. I have some sort of harm of IK over PK. So harm of this equals a harm of IK over PK. That step will not work. So this is pro P. If L equals P, the coefficient has P here. So these two are not equal anymore. So there's lots of big part coming from the well inertia.
Yeah, I mean, how to define the basis when L equals P?
Same thing. That's okay. The characteristic of K, capital K, is 0. So that's fine.
But we need to move the bracket to X on DL. So
L equals P.
By side of K. But there is no inverse.
But this is when L not equal to P. Let's talk about that later. How about that? Yeah, so when L equals P, the Frobenius acts trivially. Okay, proof of the local duality. I will need some. I will have to. Of course, I need some input from local classical theory that I'm not going to prove. So they're the following. So I need to know the cohomology of the multiplicative group. So I want to, of course, when I equals 0, the invariance of this, the Galois invariance of this, of course, is k cross, no problem. And when I equals 1, it's Hilbert 90. That everybody knows. But when the next one, I equals 2, this is really local classical theory. It tells you that the second cohomology of the multiplicative group is Q mod Z, or the people call it Brouwer group. And beyond that, it's all 0. But this can be, in fact, this one will have cohomological degree 2. So namely, for any module here, the cohomology only have 0, 1, 2, 3 terms. But somehow I realized that we don't really need that. So I just need for this particular group. That's enough. And I need another sort of relatively technical condition. So let me explain that. Or something really come from local classical theory. You probably have seen it. When L over K is a finite extension, so I have this so we know that this is sort of Q mod Z by local classical theory, the Brouwer group of L, and also there's a Brouwer group of K. There's a restriction map from this one to here, but that's not what I'm looking for. I want to say there's a co-restriction map from the Galois cohomology going this way to here. This is an isomorphism. There is a restriction map. This is multiplication by the degree. But I mean, for me, what's important? I have this co-restriction map, which I want to know that's isomorphism. This is somewhere in the proof of the local classical theory, and this will send the what's it called? Some sort of a class formation to the class formation. So let's accept these and see what we can deduce from these. I'm mostly going to, for most of the time I'm going to use the first one. Okay, this one is only used at one place. So let's do a small calculation, which I found very interesting. Well, which I found somehow this is very helpful in many cases. So let's do this. It's always important to talk about the Kummer theory. Kummer theory is very important. I consider this exact sequence, right? The Kummer theory. And then I take cohomology. What do I want to do? I want to do H1. So I want to do H1. But H1 is 0 by Hilbert 90. And this will come around to here, H2 of GK. H2 of GK. Okay, so I mean, over here, raising to L to the nth power is somehow, I guess, cohomology can think of it as multiplication by L to the n. Because this multiplication, raising to L to the nth power is just really somehow, have an element multiplied to self, so L to the n times. So you have this. Okay? And now we know that these two are both Q mod Z's. And that's 0 over there. So we deduce that this bit here is canonically isomorphic to Z mod L to the NZ. continue on downwards about this cohomology. And also we know that because it's Q mod Z, and multiplied by L to the N is actually sort of surjective to Q mod Z. Just think of it. And also later on, when I get to H3 and H4, they're all 0. So therefore, I get H. So the higher cohomology of this one is also all 0. So all vanishes. And now I can take a limit. I can take the limit of this one as n go to infinity, and I can tensor with OE for the result I get. So I will just get H2 of GK of E over OE 1 is isomorphic to Z. I mean, I guess I can take sort of direct limit to that. I can take direct limit of this one as n goes to infinity. Well, maybe this is a bad way to write it. I should have written this way, and then taking a limit will look a little bit better, more like that one. But anyhow. At least this tells us somehow. Remember, like when I state the local Tate duality, the cup product, the image of the cup product is H2, and I say that's isomorphic to the E mod OE. So that's the isomorph that I'm using. Let's see. So right, what do I do? So reductions. So now I'm going to try to prove this local duality. So first of all, and also the finiteness as well. So first of all, if so I guess for it, let me call it star. Let me just add some. Well, let's say star. Fine. I'll be mostly focusing on this isomorphism. Okay. I'll be mostly focusing on this sort of duality. The finiteness, if you look at the proof, it really also at the same time proves the finiteness. So I want to reduce to the simple case, I guess. For an exact, I want to note that for exact sequence, whenever I have sort of exact sequence and so, it's very easy to see that star for both M1 and M2 will imply star for M. Right? Because maybe I should, maybe before that. Before that term implies that I do have a cup product from GKM 2 minus I GK of M dual 1. The cup product is well-defined cohomological map. So cohomological, I guess, I don't know how to say it, but it's something that's sort of well-defined, and then I can compose with this. So I do have a well-defined map now. And now, because of the cup product, I definitely have a canonical map. I just need a canonical map from this to H2 minus I. Okay? Right now I have a map. And I'm claiming that this is an isomorphism. That's what we're going to prove. And first I want to say that for an exact sequence as so, this being isomorphism for M1 and M2 implies this being isomorphism for M. Let me think. Let me actually give the proof here. I know this is sort of very easy, but I will use the same diagram later on as well. So let's see. Let me maybe start with a 0. later on I'm gonna change to other settings. So now I'm downwards. Remember that I can write the exact sequence from the right to the left with coefficient m star 1, and I dualize everything. So now maybe I just write that first without the arrows yet. So I can write the other exact sequence from right to left for the moment. Okay. Also note that this will imply that when you dualize it, the m2 star 1 becomes sub. Okay. Right? When you dualize it, you have to swap the terms. So therefore, m1 becomes the last term. So at this moment, let me write h2 here. Right? So the exact, I read the exact from the right to left. Now I'm going to dualize everything. This will potentially go on to the left as well. Anyway, let's dualize it first, and then I'll add that term. I'm already here. So I dualize everything. Now I have to sort of change the direction of the arrows. Well, supposedly there's another term here as well. So let's just write it down. Okay, supposedly there's a term as well. And because of this functionality here, I have the corresponding map, vertical maps down. So in this situation, when we talk about the star for M1, M2, for M, we're doing it assuming this is an isomorphism. In that case, this is also isomorphism in some sense. In a sense, I also kind of assuming this H3. Maybe I should put that in. So that star also includes that somehow this H greater than or equal to 3 GM is 0. Okay. So these are all isomorphism. And therefore by sort of 5 lemma. 5 lemma, right? The middle term is also isomorphism. And then we're done. We're going to use this diagram later, so that's why I write it down here with little modification. So because of this, where am I? Yes. So we may assume that M is a KE vector space. In the sense that I can, filter it by sort of M and var pi M and var pi square M and so on and so forth, using the exact sequence like this. If you want to prove this isomorphism, it suffices to work when M is a KE vector space. And let's maybe do a very, very special case. Let's make our life extremely easy. I want to say K equals, I want to consider a case where K already contains L roots of unity. L could be P or not P, it doesn't matter. And I want my M to be just sort of KE, which is also the same as this one. I think of this sort of mu L as well. Because as scalar representations, so Galois group has trivial on this one. So it's the same as just regular vector space. And so this was, as I said, it was trivial. GK action. Oh, I'm sorry. Maybe just one. Let's see, trivial GK action, and maybe next step, because these are just vectors. Just repeat, just some sort of copies of reduced. I want to say just reduced to m equals FL. I can sort of change the coefficients as well, so that I guess because of trivial action, so therefore I don't have to take so much of coefficient field. Everything's base changed from the FL coefficient form, so I can just use FL. So let's see what the duality we're talking about here. So in this case, things are extremely easy. So this is called product. Right? I mean, this is basically this because this one is just FL, and this cup product is how to put it? It's obvious. This is a perfect pairing. This is a FL vector space, and it goes. So this is also FL isomorphic as well. I don't know how to explain it, but it's obvious. Okay, that's obvious. And so let's do something that's not quite obvious. Well, less obvious. Still very easy. Now I want to say whether that's the same as also canonical isomorphic. H1 GK. Right? So basically H0 and H1, they're dual to each other, already checked. Now H1. H1, so I have to compute both sides basically. So what are the corresponding both sides? So this is, because it acts trivially here, GK acts trivially on FL, so this is group homomorphism from GK to FL. And this is a Abelian group, so this factors through the Abelianization of this group. Okay, maybe just stop there. Let's work on the other side. Depending on how you are familiar with this Kumar theory, let me just do it here again. So what is this? What's happening here is that I want to consider mu L goes to Q7, actually L's power. Good. And then I take the Galois cohomology, so I get this goes to K cross, and then goes to H1 of GK mu L. And the next one is 0 by Hilbert 90. This is Hilbert 90 is 0, and therefore this H1K GK mu L is just K cross over K cross to the L's power. And this is something you should just know right away on the other hand. Anyways. But there's another way to write this. This is a Helm of the thing. This is a Helm of the thing too. I mean, by definition, this is a Helm of KL to QL mod ZL, but it's somehow, like, because it's already L torsion, so it's the same thing as this. And this is also the same as Helm of K cross. Because this is L torsion, I mean, like, you have to Q all the L powers as well. So what we're asking is that these two are somehow the same. And if you look at it carefully, this is precisely what the local classical theory is trying to tell you. That the Abelianization of the Galois group is almost the same as the multiplicative group of the local field. Except over here you should have taken the pro-completion, pro-finite completion. But somehow we're homing into a finite Abelian group. There's no difference. You don't see the difference. So this is because maybe I lied just a tiny bit here that somehow I also need this additional fact from local classical theory that this isomorphism, that somehow somehow the argument map is really compatible with local duality. Or rather, maybe put another way somehow, I guess a special case of local duality is our map. Okay. Anyways, so that's something we need to use as input. Nonetheless, let's assume that, so we're good. Okay. So that's all set. One final thing. H greater than or equal to 3, GK FL. Or maybe mu L. I mean, FL and mu are the same in this case. We already discussed on this board before you erased, this is all 0. By the advantage of hierarchical homology of sort of multiplicative groups. Okay? So this special case is very easy. And then my next job is to kind of bootstrap from the special case, the general 0. So I'm going to use this diagram here. Okay. Now let's move to general case. So let's see. I need okay. So let me maybe move over here. I need an input. This is one of your exercises. I think if I remember correctly, 1.4. I just added the following. So if L over K, a finite extension, and N a GL module, then I can talk about the car product. Oh, I'm sorry. Oh, I know, like in many books, so for Galois comedy, just write the field here instead of the Galois group. I'll try not to do that. I just didn't like the notation. So you can take your sort of cup product as so. But on the other hand, you can induce the GL module to a GK module, and then take Galois homology. And of course, these are isomorphic by Shapiro lemma. Oh, sorry, GK. I said I was gonna not to write that. Can't help it. I'll try not to write that. But I don't promise. Okay? And the bottom one, you can also make some sort of cup product. It turns out that induce star 1 is the same as induce n star 1. Like dual and 1 can be, I should say, it's commutes with taking dual 1. And this will go to GK. Ah, man. And the key point I want to say is that so these are isomorphism. So there's a kind of a map for this diagram. The commute, the corresponding map, is a co-restriction, and by the local class field theory, statement we needed, we talked about. So this is an isomorphism. In other words, so in your exercise, you're going to check that this diagram commutes for general cup products, and for us, this will be helpful to reduce, I guess somehow help us to kind of reduce the question of this cup product from one of the cases to another, using Shapiro lemma. We'll see to the dimension shifting. Let's see how we do that. So now let's shift to the general case. So I want to consider a general case. So let M, just let and be a general KGK module. Of course, finite dimensional. Okay. So then, because I mean the M itself is sort of finite, I guess. So therefore, you can find a finite extension, finite Galois extension, L over K, such that GLX trivialate on M. Okay? Because, I mean, like, the automotive group of M is finite, so you have to hump for GK to that, and the kernel is some sort of finite extension. You can shrink to some finite extension where the action is trivial. And also, let's put another thing. L equals to L mu L. I mean, I just make it a little bit larger. Doesn't hurt. So, from this, I can deduce the following. So, see what I want. I want put M to be on the left. So that was somehow sort of the induction we're talking about. Dimension shifting technique. Oh, sorry, this is the big induction. Yeah. Yeah. So M will be embedded into the induced representation. I first restrict this to GL, and then induce back to GK. So this is finite, and this is finite induction. So that still makes sense. And there's a co-kernel, Q. I don't care. Something. So I can always make such a construction. Now I want to use this diagram here. I wrote very small letters because I want to fit the diagram so that I can just use that. I understand this is very bad to some sort of use existing things on the board. You know, if you're taking notes, this is very bad. But anyhow, I'm do it. I'll try not to do that so many times. So I have this induced, just write induced module. I'm just going to, I don't have space to fit that, so just write induced. Okay. This is M, that's fine. This is an induced M. So this is Q due over 1. So I have this. Oh, I don't have the isomorph. Let's remove the isomorph. No. I don't have isomorphisms. No, let's have that. Oh, good? Okay, yeah. Because, I mean, why the existence of M? So, because this thing maps to, I mean, there's an automorphism of M, right? But this guy is finite. But GK acts on M. M is finite. So that means that GK maps as an automorphism group of M. But this guy is finite. So this automorphism group is finite. Right? So definitely you take a kernel of this. That's a finite index subgroup of GK. So make that extension. Sure? I did say finite dimension. I did say finite dimension. Thank you. Yes. I'm not talking about, so this is part of, I guess, a small reason why we wanted to deal with finite things. Okay. That's good. Now let's see, what do I do? Now we're going to use this Shapiro lemma. So this is because this is induced representation. So I can use Shapiro lemma. So it's induced back from GL to GK. So I want to go back to H0 of GL of M. So this is for the same reasoning, because I already so trace by 1 is also anyways. This is, in any case, this is the same as that one. Excuse me. Actually, I'm not even sure I need this, but anyway, unless I have it, make my life easier. Oh, this is GK GL of M, this is H1 GL M twist by 1. Dual. Did I have dual here? Okay, good. So now I have this corresponding map. Okay? I do need that commuter diagram to say this part is a commuter diagram. And same as well here. Okay. I need that commuter diagram to say this is the commuter diagram. So I can use this map in place of this map. But we just proved in the thing that I just erased, in a special case, that this is an isomorphism. So whenever the induced part is an isomorphism. Okay, but the induced part, because now it's Lx trivially, but GLx trivially on M. Maybe I should say this. So this is just H0 of GL of FL tensor with M. Excuse me. Maybe that was somehow the confusing part. And this is just sort of GL of the trivial one. The tensor with M twist by 1 inside. Dual and then dual. Okay. Right? So the M and M, like if you do something twice, it's just same as M. So these are all isomorph. So when it's a trivial mode, you can take out the M because there's no action here. So all these induced things these are isomorphisms. That we know already. Now let's give these some names. Just one sec. Let's see, what do I want? I want, this is number 1, number 2, number 3, and over here number 4. I mean, I don't think I would need that. Okay, here's my argument. So I have this thing, right? So now what do I know? At this moment, I don't know much, but I do know that isomorphism for the induced M terms, right? And if we have that, we already know that 1 must be injective, right? I mean, let's see. Yeah, of course, because it's already it's injective in here and here. So therefore, it must be injective here. Otherwise, if something goes to 0 here, it will already be 0 here. So anyways. So this already implies that the first one is injective. Right? And I want to comment that this is true for all M. Because when I write this diagram, I just pick an arbitrary GK module over GK module. So what I deduce is that this is corresponding H0 to this H2 dual map. It's injective for all such modules. So in particular, this says that somehow 2 must be true. Almost. Excuse me, Q must, so for Q this also holds, so this must be injective as well. Okay, now we kind of run induction. Now this is, we know this for this. Now we look at 3 here. By a version of the 5 lemma, this is enough to say 3 is injective. And once again, this is true for all M. Because for every M, I can make this diagram where I can make a sum diagram like this. This is injective, so that is injective. And therefore, I know that there's a fourth term here, which is injective, and move on. And dually, I don't have time for that. And dually, I can write a sort of diagram from here, which is sort of something like 0, and this goes to H3 of something, and then H0 of something, star, H2 of something. I can use sort of the same thing, but talking about, first of all, surjective here, for all m, and then move on to the left. But over there, I need to use some sort of a small induction. So I have to use some exact sequence like this, but to put m to the right term instead, and then to argue from the right to the left to show all the terms are surjective as well. And then by doing that, we prove that everything is isomorphism. I'll stop here.